Yeah, so hi all, good evening and welcome to the 7th week of TA live sessions for AI KRR. So before we begin, can you confirm is my audio clear and is my screen visible?
Yes, sir.
Okay, thanks for the confirmation.
Yes, sir.
Okay, thanks for the confirmation. Today we'll be discussing some questions from week 7 of the course, which is dealing with a bit of prologue, um, similar to what we did in the last week in week 6. We'll be discussing some more questions related to cuts and negation by failure and similar concepts. And then we'll move on to rule-based inference systems that includes RetainNet and such concepts. Okay, so yeah, without any further delay, let's get started. I remember there were some pending queries from the previous live session, and I think today's live sessions might get wrapped up quite quickly, so let's discuss those pending queries maybe towards the end of the session today. Okay, let's get started. So the first few questions will be related to prologue, and this is the first question in front of you. This question states that, so it gives us three clauses, C1, C2 and C3, wherein C3 is the negated goal. Okay, and we are also given two possible ways of proofs, proof 1 and proof 2, and we have to decide which of these proofs follows the SLD resolution technique discussed in the lecture videos. So just as a refresher on what SLD resolution technique is, let me show you this one slide. So what we need to focus on here is this thing. Okay, so in SLD, selected literal linear structure and definite clauses derivation has the following structure. What I would suggest, okay, you need to focus on all the points, but for this particular question I will give you a hint that we need to focus on this first point more, wherein the first resolvent has one parent from the goal and one from the program. Okay, so focusing on this particular point and these given clauses and the two proofs, which of these do you think uses SLD resolution and which one doesn't? I'll give you a couple of minutes to try to think over it, and then we can discuss the solution.
Proof 2. C. Answer C.
Okay, we have one vote for option C, which says that proof 2 uses SLD resolution but proof 1 does not. Okay, let's have a look at the question and the two proofs, and let's see whether that helps us deciphering which of these uses SLD resolution. Okay, so the first clause is not of P question mark X or Q question mark X. So this is again a restatement of the implication, right? P implies Q in a way. And then clause 2 states that P of A is true. The negated goal that we have added is negation of Q of A. Now proof 1 says that the first resolution that we are going to do is that we are going to derive Q of A from clause 1 and clause 2 by substituting this variable X with A, right? So this essentially becomes P of A implies Q of A, and then in clause 2 we have P of A, so together they imply Q of A, right? And then based on that R1, the QA that we derived in the first resolution step, and clause 3, which is the negated goal, we arrive at this empty set, right? So this is proof 1. What proof 2 does is it first uses clause 1 and clause 3. So P implies Q and not of Q is available to us So what can we derive from that using modus tollens? Not of P, right? Are you with me? Any doubts here?
What, sir, again?
So in proof 2, we are given P imply. So in proof 2, we first use clause 1 and clause 3, okay, in resolution step 1, okay. P implies Q is given to us, and we are using not of Q, okay, by substituting X with A. So what can we derive from that? P implies Q and not of Q.
Negation PX.
Negation P, right? P of A,
Yeah.
negation P of A, because we are doing
No.
this substitution.
X is more. Yes.
And again in the second resolution, we use negation of P, PA, and then PA from clause 2 to arrive at this empty set, right?
Yeah.
So both these proofs are actually sound. They do make
Yeah.
sense, they follow the logical steps, but how will we decide which of these use SLD resolution or not?
So because in proof 2, we have taken one from parent and one from the goal.
That is right. So, um, like I mentioned, in one of the important points about SLD resolution is that, or SLD derivation is that the first resolvent has to have one parent from the goal, right, which is clause 3 in our case, and one from the program, which is the clause 1 and clause 2 given to us, right. And if we have a look at the two proofs, proof 1 uses clause 1 and clause 2 in the first resolution, right. Both these are the parent, the two clauses, the programs given to us, right. So the parents are coming from the two C1 and C2 and not from C3. But like one of your colleagues mentioned, that SLD resolution should require one of the parents coming from the goal itself, which is C3. That's why proof 2 uses SLD resolution, but proof 1 does not. I hope that's clear. Any doubts there?
Sir, in SLD, can we use the parent rule more than one time?
So these are the three things that we have to be careful about. One, as long as these three things are fulfilled, I think any other liberties we can take. So the first thing is the one that we just discussed. The second point is each resolvent in the derivation is negative. This is equivalent to doing backward chaining. And the third is the latest resolvent becomes one of the parents, and the other parent is a positive clause from the program. So I think the third point gives some hint towards your question. The latest resolvent that we come up with becomes one of the parents, and the other parent is a positive clause from the program. So once we arrive at a new resolvent, we have to use that in the next step. Does that answer your question?
No, sir, not clear.
So I think what you meant to ask is, can we use the same two clauses or same two or three clauses again and again for resolution? Is it?
Yes, sir. Yes, sir.
Yeah. So we
From the
can't do.
parent, not for goal. From parent.
Yeah, we can't do that because see, the first step needs to involve the clauses from the program and one parent from the goal, right? And
Yeah.
then once we proceed with that, let's suppose in the second step itself we don't have the empty set, so we need to keep doing these resolutions, right? So
Yeah.
we need to include the resolvent in the previous step in the next derivations. This is what point 3 mentions here. The latest resolvent becomes one of the parents, and the other parent is a positive clause from the program. Okay, so we can't keep on repeating the same resolution in every step.
Okay, sir. Thank you.
Okay, thanks for your question. So Yeah, I think that was question 1. Let's move on to question 2. So question 2 is about negation by failure. Okay, so this says that let P denote an atomic formula in first order logic, then negation by failure, which is represented by this slash plus of P in prologue. Which of these options do you think is relevant to negation by failure? So this is kind of a recall based question from the prologue part of the course, and yeah, this is a recall based question, but the next couple of questions that we'll be looking at, maybe 3, 4 and 5, those will be applications or intuitive questions based on negation by failure. So yeah, that's just a hint. So what do you think about this question? Which option do you think would be correct? Okay, we have one vote for option B. So I would again give you a hint to focus on the term negation by failure. Okay, so what this gives us an idea of is that when all attempts to prove P fail, right, what should it return? Remember, it's negation by failure. So we are kind of failing to prove P by all possible means. Wouldn't option C be more appropriate in that sense?
Yes, sir. C. C will be correct.
Right? So negation by failure basically says that in prologue, when P is an atomic formula, negation by failure returns true when all attempts to prove P fails. It also returns false when at least one attempt to prove P succeeds. Okay, so the correct option here would be C and D. It's okay if there is a little bit confusion about this concept as of now. Hopefully when we discuss the third question, which is about negation by failure, it will get a bit more clarified. Okay, okay, let's have a look at question 3 then to bring more clarity into this. So question 3 gives us a prologue program. Okay, here we have defined link x comma y. This basically defines that there exists a direct link from x to y, and then root x comma y defines that there exists a path that contains one or more links from x to y. Okay, so for example, let's say there are two positions x and y. If they are connected by a line, we say that there is a link between x and y. If let's say there is a line between x and z, x and y, and then another line from y to z, then we say that x and z are connected by a root, not only one path, or not only one link, or more than one links. Okay, you must also note that root containing a single link is also a root, right? So here we have defined root on the left hand side. So root x comma y, if so there is a root between x and y if there is a link between x and y. That is what the first line tells us. And the second line tells us that there is a root between x and z if there is a link between x and y, where y is some intermediate node, and there is a root between y and the final node, which is z. Okay, so this is the definition of root, and then we are given two facts, which is link a comma b, so which means that there is a link between a and b, link a comma c, which means that there is a link between a and c, And then we are given one negation by failure statement as well, which says that there is a link between B and some node y, where y is a variable, if we arrive at a negation by failure of link a comma y. Okay, so this is the information given to us. We have to select the queries that return true or they return one or more solutions. So we have to we have to select the specific options that will either return true or return one or more possible solutions to the query that we put in Prolog. So if you have a Prolog system right now in your system with which you are connected, I would highly encourage that you try to test it out right now itself. If not, you can use your intuition to see which of these might be the correct options. I'll let this be here for a couple of minutes and then we can discuss the solution. Okay, any guesses of about which of these options could be correct? Okay, so we have a vote for options A and E. What about the others? Okay, let's look at the options one by one and let's see what we might expect when we query each of these. Okay, so let's consider the first option, which says that link a comma y. So this basically asks so we are basically asking the Prolog that what are the points or what are the nodes with which A is linked to. Okay, so based on the facts given to us, specifically these two facts, what do you think will be the output of link a comma y? Remember that we are already given that A is connected to B and A is also connected to C. The outputs of link a comma y query will be link a comma b and link a comma c, right? Do you agree with me?
That means instead of Y, we can take B or C.
Exactly.
Okay.
So basically this capital Y is a variable for Prolog, right? So it will give us the various options that we can fill in this variable Y with. It's similar to one of the questions that we discussed last week, the last question in the last live session, remember? This question was basically about appending two lists to make a new merged list, and then we asked Prolog what are the different ways in which we could merge these two lists to arrive at the final list, right? So here also Prolog will list all the options or all the different solutions that could exist for this query link a comma y. Okay, it will give us two solutions based on the two facts given to us. So option A will be correct. Now let's think of option B. Here we are querying link a comma e, where both a and e are constants. This is not given to us in the knowledge base. So what do you think will be the output in this case?
If it will be some by negation as failure, this will be true, I think.
No, we don't have
No,
to apply
because of,
negation by failure over here. We just
no,
have
why?
to,
Yes, sir.
we are just checking whether there exists a link between A and E, right? And based on the facts given to us, so this is what we have provided as information to Prolog, okay? Out of which the first two lines are definitions of root, okay? And then the next two things, link a comma b and link a comma c, these are facts. And then this is sort of a semi rule or a semi fact which allows us to check whether there is a link between B and another node given negation by failure with another basic condition, okay? But in this particular query we are not checking whether there is a link between B and something, right? So we need to worry about negation by failure only when we have to check a link between B and another node. Here we are checking whether there is a link between A and E. We are only told that there is a link between A and B and A and C. So the output of this query B should be false. Do you agree with me?
Yes, sir.
Okay, so B will be false. Now let's look at, so we'll come back to option C. Let's first look at option D, because option C and D are kind of related to each other. Only that in option D we are checking whether there is a root between two constants, and in option C we are checking whether there is a root between A and a variable y. Okay, so yeah, let's see whether there exists a root from A to E. So let me actually show you a trace that we will expect when we use Prolog to inspect this. Okay. Yeah, that is better. So here we are examining root A comma E. Okay, so it will go into the definition of root. Okay, so let's check what the definition of root was. Root first checked whether there is a link between x and y. Okay, so that is what it will check first. The root A comma E will make a call to link A comma E. Okay, and this will fail because there is no link between A and E, which we just saw in the previous option, right? So this will fail, and then we will go back to the definition of root A comma E, right? Now basically what has happened is this first line of the definition has failed. So we will now check the second line of definition for root. Okay, and this involves two steps. First, checking whether there is a link between x and some intermediate node y, and then whether there is a root between that intermediate node and the final node. So that is what is happening over here. First, there will be a call to check a link between a and some intermediate node that is represented by this alphanumeric, which basically represents a variable. Okay, and then given the facts to us, we know that there is a link between a and b, right? So that is what is shown in this line over here. Now it will go to the next step of the definition of root, and it will check whether there is a root between b, which is the intermediate node that we arrived at, and the final node, which is e. Now we have to check whether there is a root between b and another node, and now we will have to encounter negation by failure, right? So basically this line tells us that a link exists between b and another node y if we have a negation by failure of link existing between a and another variable y. So that is what is happening in this trace again. We first check whether there is a link between b and e. To check that, we check whether there is a link between a and e, and we know that this is not true, so this will fail, right? And now we see that all attempts to prove this particular a link between a and e have failed, right? So this is an example of negation by failure returning true, right? So this will go back to link b comma e, and link b comma e will return true. Since there is a link between b and e, we will say that root b and e is also true, and finally root a and e is also true. So eventually this query will output true. So this is also an example of how you can use trace to understand what exactly is going on behind the scenes when you make a query in Prolog. Okay, and I highly encourage all of you to try to practice this, not just with this example, but with different examples, both in the practice assignments as well as the graded assignments, so that you can have a better understanding of the behind the scenes of Prolog, and this will be essential when you solve the final exam. So is it any confusion on why root a comma e will be a correct option? Any doubts there? Okay, I hope there are no doubts. If there are, please feel free to let me know. Please feel free to unmute yourself or post your doubt in the chat box. So if we are clear on why option D is correct, then by the same logic we can we say that option C is also correct? Anyone?
Sir, root a comma y is the option C. Am I right, sir?
That's right.
And based on the first one, root of a comma y, if there is a link between a and y, can I take it that way?
Yeah, based on the first line of the definition
Yes.
of root, right? Yeah, that's how it will proceed.
Yes, sir. And there is a link between a and b, and there is also a link between a and c.
That's right.
How can I complete that, sir? The first part.
So let me show you the workflow of how it will be done. So when you first query root a comma y, it will first check the it'll go, so it'll move in the order in which the facts are, or the facts or the information is given to Prolog. Okay, so let us number these. So let me copy this and paste it here. Okay, so this is the first thing given to us. This is the second line. This is the third line. This is the fourth line, and this is the fifth line. So this is the order in which we are given information. We are giving information to Prolog, and then we are querying whether there is a root between a and some variable y. Okay. Now Prolog will first will process information in the order in which we give information to it. So first it will check the first line that we have given to it. So first it will check whether there is a root. So it will check that root exists between a and y if there is a link between a and y. Okay. Next it will check whether there is a link between a and y, and there is a link between a and y that it will query, and the answer to this query will be link a comma b. Right, because that is the first fact given to us.
Yes, sir.
Okay. Okay. Now that is done, so now we are actually checking the second line of the definition, because so the first line of definition failed to give us a concrete answer because y is still a variable. So we shifted to the second line of definition, which is there exists a root between x, where x is a, z, which is the, in this case our final node is some node that we don't know, y, right? It will first check whether there is a link between x and some intermediate node, and then check whether there is a root between that node and the final node. So now that we have an answer that there is a link between a and b, next what Prolog will try to check is whether there is a root between b and y. Are you with me till here?
Yes, sir.
Yes, sir.
Yes, sir.
And now to check whether there is a root between b and y, we again have to follow this negation by failure logic. Okay. So to check whether there is a root between b and y, we will first check whether there is a link between b and y. To check whether there is a link between b and y, we will try to do negation of failure of whether there is a link between a and y. Okay. So we will see that all ways of proving that there is a link between a and y have failed if we consider, let's say, y equals to e, which is the fourth option given to us, in which case y will be replaced by e everywhere. Right? To check this, we have to check whether there is a link between a and e, and then this will again return false, and there are no other ways in which we can fulfill this. So this will return so all ways of proving a link a comma y have failed, so this negation by failure will return a true. So link b comma e becomes true, hence root b comma e becomes true, right? And because of this, root a comma e becomes true. Okay, so this is the flow of the procedure in the fourth option. Is this much clear?
Yes, sir. Yes, sir.
Okay, now in the third case where we had a comma y was not necessarily e, it will follow a similar logic, right? So here again we will have y everywhere. It will check whether there is a root between b and y, then it will check whether there is a link between b and y, it will check whether there is a link between a and y. Yeah, if it will be great if you can mute yourself if you don't have a question. Yeah, thanks for that. Now in this case there is one way in which we can prove this, right? Because there is a link between a and c. Right, so because there is one way in which we can prove this, so this will return false. Negation by failure will return false, right? So link b comma y will be false, and because of that root b comma y will also be false, and consequently root a comma y should also be false. Does this make sense?
Yes, sir.
Okay, so let's go back to our options then. So yeah, so while doing this derivation I realized that option C should actually be false. I think in the answer we have marked it as correct, so please make a note of that when you revisit the slides from this live session. So option D will be correct. Option C I think will be wrong. What about options E and F? So note that option E is similar to option C, option F is similar to option D. So this is what we'll get when we query link b comma y and link b comma e. Okay, link b comma y will again follow the procedure that we just discussed, right? It will check whether there is a link between b and some variable. To check that, it will check whether there is a link between a and some variable, and it will see that there is actually a link between a and b. So negation by failure will return a false, and so this query will return a false. Whereas in case of link b comma e, it will first check whether there is a link between b and e. In order to check that, it will check whether there is a link between a and e, and this will fail because we know that there is no link between a and e. So negation by failure will return a true, and hence this query will return a true. So the correct options would be A, D and F. C should be marked incorrect, so please make a note of that. I will correct that in my slides as well. let me move to this actually. Yeah, the correct options will be A, D and F. C should be incorrect, okay, and I'll make that correction. But yeah, other than that, A, D and F are the correct answers. Okay, so any doubts there, or should we move on to the next question? Okay, if there are no doubts, then maybe we can move on to question 4 then. So now we are done with negation by failure. Now we are going to discuss something that is called cuts in Prolog. Okay, so here basically what we are given is two definitions of this remove all predicate. Okay, what remove all predicate does is it removes all instances of a particular element from a given list. For example, let's say there is a list that contains 1 comma 2 comma 3 comma 2. Okay, note that 2 is occurring twice in this list. So what we want the remove all predicate to do is to remove both occurrences of the element 2. Okay, and the output of the whole program should be 1 comma 3 alone. Okay, this is what we want to achieve using the remove all predicate, and here we have defined it in two different ways using two different kinds of cuts. We have to identify which of these is a green cut and which of these is a red cut. Okay, let's go over the definitions of the two predicates once. So let's go over remove all 1 first. So remove all 1 tells us that if we have to remove an element E from an empty list, it will output an empty list. That makes sense, right?
Yes, sir.
Okay, the next line of definition says that in a list where the head element is marked by H and the tail part is marked by T, if we have to remove the element E and the output would be something called ZS, this happens if E is equals to H and then there is a cut, and then which recursively call the remove all function on the tail part of that particular list. So I'll give you an intuition of what exactly does cut do. So suppose we have defined something in Prolog in this way. This is one part of the Prolog definition. This part, let's say part A, happens if a condition is satisfied, let's say B, and then let's say we have a cut, and then there is something else, some other definition or some other thing to do, that is C. Okay, so whenever this part B evaluates to true, right, what if there is a cut present over here, the Prolog program will transfer the flow of the program to part C. Okay, it will act as if this cut was not there, so it will go from B to C. If however let me if however this evaluates to a false, then what this cut will do is it won't let the flow of the program go to C. Instead, it will directly go to the next line of definition, which might be something else. A is true if some other condition, let's say B1 something. Okay, so that is essentially how cut works. So is this part clear about the working of the cut operator?
What, sir?
Is the explanation on how exactly a cut works in Prolog, is that part clear?
Yes, sir. Sir, this coat is green coat or red coat?
That we have not yet decided. As of now, let's just first understand whether how a cut works, okay, and then we'll look into what is a green cut and a red cut. Okay, so is this part clear?
Yes, sir. Yes.
Okay. So if this is clear, now let's go back to the question that we had. What this second line will do is, if this condition E equals to the head element of the list, if this is true, this cut will allow the flow of program to go on to this part. If this condition is not true, this cut operator will transfer the flow of the program to the next line of definition, which is this one. Okay. Now let's talk. Yeah, is there a question?
Sir.
Okay. Now let's understand what is a green cut and what is a red cut. Now sometimes when we have a cut present in the Prolog program, we get a certain output. Okay. Suppose we remove that cut from the Prolog program. If the output still remains the same, irrespective of whether we had the cut or did not have the cut, that will be a green cut. If, however, removal of the cut from a Prolog program changes the output that we get, then we will call it a red cut. Okay, so suppose if you remove this cut from here, if the output of this remove all one predicate still remained the same, which means it's a green cut. If, however, after removal of this cut operator, the output changed, then that means this is a red cut. Okay, so is the difference between green cut and red cut clear?
Sir, please give an example.
So, so an example is this question itself. We can consider a simple list. Okay, let's say the list is 213. Maybe I'll write that down. 213. Okay, and we want to remove the element 2 from this list. Remember that we are writing a program to remove all occurrences of a particular element from a list, but for simplicity let us assume that there is only one occurrence of 2 in this list. Okay, now you go through the definitions of the two remove all functions given to, or remove all predicates given to us, and see whether the output remains the same with or without the cut operator, and that will give a hint about which one is a green cut and which one is a red cut. Okay, so I'll go back to the definitions over here, and I'll leave this on here for a couple of minutes, and yeah, then we can discuss the solution. But I would highly encourage you try it out first yourself. So while you're thinking about it, I'll just go and get some water, and then maybe once I'm back we can discuss the solution. Okay. Um, so any guesses or any partial solutions on which of these could be a red cut and which of these could be a green cut?
Answer is B.
B. Okay, we have one vote for B. Let's have a look at the solution then. So let's first consider the remove all one definition, and let me copy this over here so that we can refer to it readily. Okay, so what this tells us is that, so we want to remove this element 2 from this list, 2 comma 1 comma 3, where 2 is the head, 1 comma 3 is the tail. Okay,
Sir, list 2 and 3 is given.
yes, 2 1 3 is given to us.
Sir, where, sir? In question there is no 2 and 3.
No, in question it's not given, but we have to assume a toy example to decide whether this contains a green cut or a red cut, right? We have to come up with an example. Otherwise, how will we decide?
Okay, it's an example. Okay, sir.
Yeah, this may not be 2 1 3. This could be 4 5 6 also, but we have to come up with some small example to decide whether this is a green cut or a red cut, right?
Okay, sir.
Yeah. So now let's walk through the different lines of the definition of the removal predicate. So the first line tells us that if we remove an element E from an empty list, it will give us an empty list. This is not applicable in our case because we don't have an empty list. So we'll go to the second line. The second line tells us that if we remove an element E from a list in the form of head represented by this element H and the tail part represented by T, the output should be ZS if, so the first condition is E equal to the head element. Okay, so our E is 2, and is E equal to H?
Yes, sir.
Okay, yeah, E is equal to H. So please feel free to tell me to slow down if there are any doubts. Okay, so coming back to the solution then, yeah, so now that we know that E equals H is true, and we also have a cut after this condition, because this condition evaluates to true, what do you think will happen? The flow of the program will move to the next part.
Yes, sir.
Right, so then we will check whether we will recursively call the remove all function on this part. Okay, so we will have E, which is 2, the tail part of the list, which is 1 comma 3, and then some output ZS. Okay, again this has the head element as T, head element as 1 and the tail as 3, right? And again we'll recursively call the remove all. In this case, E is not equal to H, right? Because E is 2 and
Yes.
H is 1.
Yes, sir.
So now because of this cut, where do you think the flow of the program will go?
It will go to the next line.
Next line, right? So then we will check remove all of 2, head element will remain as is 1 comma 3, and the output we will add the first head element, because we know that that is not something we want to remove from the list. Okay, and this will be true if we recursively check this part. So 2, and then the tail part, which is 3 alone, and this would be ZS. Again, we will recursively apply remove all, in which case this is the only head, there is no tail, tail is empty. Head and E are different. So again, we will in the output, this will be empty, and we will have 1 comma 3 comma ZS. And again, we see that head and the E element 2 is not the same, because head is empty and 2 is E. So now we go back to the definition of removing something from an empty list. So this will return an empty list. ZS will be empty, so our final output will be 1 comma 3, right? So this has removed 1 comma 3. This has removed all occurrences of 2 from the list, and we are left with 1 comma 3. Okay, now let's remove this cut operator. And now let's repeat the same thing and see whether the output remains the same. So the first thing that we're going to do is remove of 2, it's already written, so maybe I won't write it again. This is what we want to check, right? And we see that the first condition matches as per the second line of the definition. There is no cut, right? So we will straight away move on to this part without even thinking. Okay, so next we will examine 2 comma 1 comma 3 ZS, right? Again we will call remove all. Okay, in this case E comma H does not match, so this will return a false. Despite it returning false, we will still move to this part, right? Or maybe it will just terminate over here because this is false, so it will end up giving us false or an erroneous result based on going to this particular operator despite this being false. In any case, the output of removing the cut operator and the output with having the cut operator are the same or different. Anyone? So the right hand side is the output that we got with the cut operator. The left hand side is the output that we will get when we remove the cut operator, and these two outputs are different. So what does that tell us about the type of the cut?
Red cut.
Red cut. That's right. Does everyone agree? Okay, thanks for the confirmation. That's great then. So we have established that the cut used in remove all 1 is a red cut. Now for remove all 2, I won't solve it completely, but I will encourage you to solve it with the same example that we just discussed, which is the list is 213 and the element to remove is 2. You keep the red cut in one instance, if you keep the cut in one instance and then you remove the cut in another instance and see whether the output changes or remains the same, and once you solve it, you will see that the output remains the same, because of which we will conclude that remove all 2 contains green cuts. So the correct answer would be remove all 1 contains red cut and remove all 2 contains green cuts. Okay, I'll leave this on here for a while so that you can verify the remove all to part yourself. So I'll leave it on here for a couple of minutes and then we move to the next question. And in the meantime, if you have any doubts, please feel free to let me know. Jaiprakash, did you have a question?
Sir, no, sir, no, sir.
Okay, no worries. So maybe I'll just mute you or you can mute yourself.
Okay.
Okay, thanks for that. Okay, then shall we move to the next question then?
Yes, I'll go to next.
Okay, then. So this is the last question from prologue. Okay. We have been told to study the following program without using tabling. And so actually this is actually a very straightforward question if you think about it. We are given a predicate that defines whether there is a direct link between x and y. Okay, we are told that there is a link between a and b. We are told that there is a link between a and c, and there is a link between b and c, and we have recursively defined that there is a link between y and x if there is a link between x and y. Okay, now we are going to feed this information to prologue and we are going to query different things. So whenever we query these different options given to us, do you think the program will terminate or whether it will go on in an infinite loop? So the hint here is the way we have defined the definition of link. So I'll give you a hint. So the definition of link that we have supplied to prologue is a cyclical definition. In order to check whether there is a link between y and x, we have to check whether there is a link between x and y. In order to check whether there is a link between x and y, again we have to check whether there is a link between y and x, and vice versa. So this process keeps on continuing. So do you think this program will terminate, this query will terminate, or will it go on forever?
This cycle is not terminate, sir.
Okay, so we have one vote that says that it won't terminate. What about the others? Does everyone agree that it won't terminate? Can I have a show of hands that says that? Yeah, so in chat box, Kushagra says that it will run till memory stack is not full. Right, that's right. So basically, it will keep on continuing in loop until we exhaust all the resources available to us on the system on which we are running this program, right? And the answer to this question then becomes that none of these queries will actually terminate. So for the first two queries, it's pretty clear, right? Because there is a variable involved, and this will keep on going back and forth between the two definitions that we provided to of link that we provided to the program. Even in case of link a comma b, it will try to keep on checking whether there is a link between b and a and b and a and b, so on and so forth. So it will also not terminate. And E and F similarly for the same reason, because that is the way we have structured the definition of the predicate link. So the answer is none of the above will terminate. And I will highly encourage all of you to test it out yourself on Prolog. Okay, so this question kind of ends the questions we have on Prolog. One advice that I have for your assignments as well as your final examination is that Prolog seems like a tricky topic to understand and master in the initial few weeks, but if you actually get a sort of a hack about how Prolog works, using the trace function and so on and so forth, by more and more practice, it becomes easily one of the most scoring areas in your exam and the assignments. So I would highly encourage you practice all the questions about Prolog that we have discussed in Prolog itself, and see basically what goes on behind the scenes. Okay. Okay, then let's move on to the next topic, which is rule-based systems. So now we are in the territory of rule-based systems, and the first such question is related to the rate init, and this question asks us, in rate init, refactoriness refers to which of the following? So this is kind of a recall based question. So which of these do you think would be the correct option or options? So just as a refresher, I'll show what refactoriness is. So basically what happens is, so in rule-based system we have a set of patterns. Okay, we match that pattern with some certain with the precursors of certain rules, and if those and if that match happens, we fire that rule. Okay, but it might be that we might encounter a situation where multiple rules are eligible to get fired, and that results in a conflict. We have to select one such rule that we want to fire or want to execute, right? And we have to find a way to choose one of those rules to execute in the next round. And there are different ways to resolve that conflict, and one of that ways is refactoriness. So yeah, so this is a slide directly from the lecture videos. And what this basically tells us is that it's not right if the same rule keeps on getting fired again and again, right? So if let's say there are a lot of matches of a particular rule with the patterns in the working memory or data given to us, we don't want the same rule to keep on getting executed again and again. And that is what refactoriness refers to. A rule instance may fire only once with a set of matching working memory elements. Okay. With that in mind, which of these options do you think would be correct?
Option B.
That's right. The correct option would be option B. We are blocking the same rule data pair from firing again and again. So any doubts about rule-based systems or working memory or the basic idea behind RetinIt? So because the next few questions are going to be based on these kind of conflict resolution strategies and the RetinIt. So it's better if we have a somewhat of an understanding to begin with. Okay, so I'm assuming that this is clear. In that case, let's move on to question 7. So question 7 gives us a production rule in the OPS 5 like language, which you might have encountered in the lecture slides, along with the working memory, okay, and the timestamp associated with the element in the working memory. Okay, we will allow the system to fire all the rules to the point that it can, and once there are no particular rules that it can fire, it will halt. Okay, so let's have a look at the working memory. Here we have only one element which says that the number 1 and sum 1. Okay, so in OPS 5 like language we have different elements, right? And these are basically the values assigned to these attributes or num. Let me actually show that structure to you. Yeah, so this is what I was trying to refer to. So whenever we mention a working memory element, we will have a timestamp associated, we will have a class name, okay, we will have attributes that will be marked by this upward arrow just before them. Okay, so rank is an attribute, student is an attribute, index is an attribute, value is an attribute, and then the value immediately following an attribute will be the value assigned to that attribute, right? For example, here the value assigned to rank is 1, here the value assigned to student is Sangeeta, the value assigned to marks is 97, and the value assigned to rank is nil. Okay, so this is the structure of the working memory elements as per the OPS 5 language. Now let's go back to the working memory given to us. Here we had the class name row, the attribute num with value 1, and the attribute sum with value 1. Now the rule given to us is this whole thing. The first part is the name of the rule, which is called fun rule. Okay, the second part is the precursor or the precondition that must be satisfied in order for us to execute this rule or fire this rule, which says that for a number a and sum b, the sum must be less than 10. If the sum is less than 10, or this value of b is less than 10, then we can fire the rule and make these changes and add these things to our working memory, which is represented by this make over here. What we do is we swap the number with the value of the sum in the previous step and then replace the value of sum with a plus b. Okay, so this is what the rule is, and this is the working memory given to us. Now I will encourage all of you to try to solve this by hand right now and tell me when the fun rule or when the production system terminates and how many times is fun rule fired. Okay, so I'll give you a couple of minutes to try to solve this. and we already have an answer in the chat box, but I'll wait for a couple of more seconds and then we can discuss the solution. Okay, we have a couple of answers in the chat box. Now let's have a look at the solution. Or first, let's try to solve it on our own.
So number of times it is 8. Yeah, 9.
Let's have a look at that. We have both answers in the chat box. Let's see which of those is correct. Okay, so this is the working. There should be memory. So the first thing that we have is num is, so I'm not writing the whole thing, but you can get an idea. Okay, number is 1 and sum is 1. Here sum is less than 10, so we fire the rule and we add a new element to the working memory. In this case, sum becomes 1 and the number becomes 1, which is this value over here, and then the value of sum becomes this one plus this one, which is 2. Now this 2 is also less than 10, so again the rule will be fired and the new element added would be number becomes 2 from here, and then sum becomes 1 plus 2
Plus 3.
which is 3. Again 3 is less than 10, so again the rule will be fired and then number will become 3 from here, sum will become
5.
2 plus 3, which is 2 from here and 3 from here. Again 5 is also less than 10, so again the rule will be fired and then number will become 5 and sum will become
8.
8. That's right, which is 3 plus 5. 8 is also less than 10, so again rule will be fired. So here number becomes 8, sum becomes
13.
13. Now sum is greater than 10, so now we can't fire the rule anymore. Now we halt. So how many times was the rule fired?
5 times.
5 times, right? First time over here, next time over here, third, fourth, fifth, and then we halted. So this is what is also written over here. Okay. So any doubts in this question or how exactly the production system works? Okay, thanks for the feedback. It's great if this is clear. Okay then. Now let's move on to the next question. So the answer to this question was 5, like we just discussed. Okay, this is another follow-up question. The last value of the sum attribute is, based on our solution, what do you think was the last value of the sum attribute?
13.
13. That is where we halted the program. Okay, now we come to RateInit. Okay, so RateInit is basically a way of representing these different rules given to us. Okay, as well as the working memory elements. So here we represent this in terms of a graph. Okay, how we can read this graph is something that I'll tell you. I'll give you an example of how to read a graph, read this RateInit graph. Okay, so suppose let's focus on this particular node. Okay, this has a number of arrows coming into it. This is one arrow, this is one arrow, and then this is one arrow. Okay, now we have to check what are the nodes that are connected by these three arrows. This one is connected by this thing, tire equals slick. Okay, this arrow is connected to this node, which is limit equals to 1, and then this is connected to this node which says that HP greater than equals to 700. So these are nothing but the preconditions of a particular rule. Okay, so if you follow this particular direction, this basically tells us that if wheel represented by V has a tire of type slick, this is one condition. If the passenger limit of that particular car is 1 following this direction, this is the third condition. And if the power capacity of that particular car has horsepower greater than 700, this is the third condition. If these three conditions match, then we can say that the car is a Formula 1 car. Okay, so this is an example of a rule represented in terms of a RateInit. Is this clear? Any doubts in this thing till now?
No, sir.
Okay, if that is clear, then let's take one more example. So there are different kinds of nodes in this RateInit. Okay, some are called alpha nodes, some are called beta nodes. So this yellow colored nodes are what are the beta nodes. This B1, B2, B3 and B4, and these essentially are representing the rules. Okay, and the others, the alpha nodes, all these A1s and A2s, these are the alpha nodes. These represents the different precursors to the rules or the facts. Okay, so now that we have understood Formula 1 car, let's take a look at another possible rule, which is, let's say, regular car, just to understand. So can someone tell me what are the conditions that need to be satisfied in order for us to tell that a car is a regular car? Based on this RateInit given to us.
Mechanism by which data and function
It should be rule 3, am I right, sir?
Yes, rule 3.
Yeah. So it should, the wheel should be of type regular,
That's right.
and it should be a passenger car with a limit of 4.
That's right.
And the power should be greater than 100, and it should be less than 300.
Perfect.
Yeah.
So that is the right way to read this particular RateInit for this particular rule. This arrow tells us that the type of the wheel should be regular, the limit of passengers should be 4 is given by this arrow, and then the horsepower should be between 100 and 300, both included. That is shown by these two arrows over here. Right, so this is how we basically read the RateInit. And now we also have a working memory associated with this problem. Okay, and this tells us the different facts about the problem. Okay, for example, the first fact, so this is the timestamp. Okay, this is the power. um, this fact tells us that in timestamp t on 201 we have some car with power, also the car is denoted by this code C37, and that the power of that C37 car is 200. Okay, similarly, 206, the fact 206 says that the wheel type of the car represented by this code N34 is regular. Okay, and then 209 tells us that the passenger limit on the car represented by N34 is 4. This is how we interpret the facts given to us. So if this is clear, then we can move on to solving questions based on written it. Thanks Kushagra for your answer as well in the chat box. I just noticed that. Okay, so the first question about this written it is, according to regular car rule, which of the following is true about regular cars? I think we just discussed this. It has to have regular tires, the passenger limit should be 4, and the power should be between 100 and 300 horsepower, based on the 4 arrows that we just saw. So the correct options are A, C and D. Any doubts there?
No, sir.
Okay, great then. Also thanks for your answers in the chat box. Okay then, if this was clear, let's move on to the next question. So now that we have learned how to identify or understand or interpret the rules given in the RateNet, and also to interpret the facts given to us in the working memory, now we have to see what are the matches between the working memory elements and the preconditions for the different rules given to us. Based on that, we will have different candidate rules that we could fire, and those will form a part of our conflict set. Okay, so this question asks us which of the following will occur in the conflict set. So here what we are given is, this is the rule name, basically F1 car, and these are the working memory elements that we will use or that will support the firing of this particular rule. So which of these do you think would be occurring in the conflict set in the first go, in the first round of pattern matching? So I'll just show the RateNet and the working memory element quickly, and you can take a screenshot or a picture of this, because we will be keep going back and forth between the question and this diagram. Okay, I hope you have taken a screenshot or a photo. Now let's go to the question again, and now you tell me which of these do you think would be competing in the conflict set.
Sir, what actual conflict set?
Okay, so let me try to explain with this example itself. Okay, so the first option A tells us that this rule is F1 car, and the elements that we are going to use is 204, 205 and 210. Let's look at what those elements are. 204 tells us that there is some let me actually shift to the whiteboard, that will be easier. 204 tells us that there is some car K32 with horsepower 800. Okay, that is one fact given to us. The other fact that we want to consider is 205 and 210. So let's make a note of that. 205 tells us that the wheel type of this car K32 is regular, and then 210 tells us that the passenger limit of K32 is 2. Now based on these three facts, can we fire this rule F1 car? Remember, the preconditions of the F1 car is that the tire has to be slick, limit has to be 1, and horsepower has to be greater than 700, greater than equal to 700. Here the facts given to us are that this car 32 has tire type regular, which is not matching because the tire type should be, or wheel type should be, slick. The horsepower is 800, and the horsepower for a Formula 1 car should be greater than 700. So this is matching.
Yeah.
And then we have said that the limit of this car is 2, but for a Formula 1 car the limit should be 1. So the conclusion is that the preconditions for this rule are not matching. Do you agree with me?
Yes, sir.
So we cannot execute this particular rule based on this combination of facts 204, 5 and 10.
Yeah.
Okay.
Yes, sir.
So we cannot fire this rule. So this rule will not go into our conflict set. Let's look at a rule that will go into our conflict set. Let's
If
look
it will fire, then it will go to the complete set.
Yes, if we can fire it, it will go to the conflict set. Now there can be multiple rules that you can fire at the same point of time. So a conflict set will be basically a set of rules and the associated patterns matched in the working memory that we can fire at a given point of time. There could be multiple such pairs. What we have to do in the next when we do the conflict resolution is we have to select one of those rule and pattern tuples. Okay.
Okay, sir.
But based on how we decided that F1 car is not something that will be in the conflict set, can you tell me whether the other options will be a part of the conflict set or not? So the second option is luxury car with 204, 5 and 10. Okay. So the car still remains the same, the one that we saw in the previous options, which is this K32 with horsepower 800, wheel type regular and passenger limit 2. Let's look at regular car. So regular car has wheel type regular, which is matching. The horsepower should be for regular car should be for luxury car we are looking at luxury car, right, not a regular car. So for luxury car, again wheel type should be regular, horsepower should be greater than 700, which is also matching, and the limit should be 2, which is also matching. So can we say that luxury car can be fired?
Yes. Yes, sir.
That's right, it can be fired, right?
Yeah.
What about the other options? Regular car, minivan, and minivan again, but different set of rules, different set of elements. So let's have a look at the other options as well. So option C tells us that we need to check for regular car with elements 203, 6 and 9. So let's check that. Let's remove these things. The facts that we are given are 203, 6, and 9. So 203 tells us that there is some car N34 with horsepower 280. N34 has wheel type regular, and then N34 has passenger limit 4. These are the facts given to us, and we have to classify whether this is a regular car or not. So the conditions of a regular car are that wheel type should be regular, which is matching. The limit should be 4, which is also matching, and then the horsepower should be between 100 and 300, both inclusive, and the horsepower is 280, which falls in the range. So can we say that regular car can be fired?
Yeah.
We can say, right? So regular car is also a part of the this particular option is also part of the conflict set. Then the next option
Also an approach to programming. There are different
Sir, I have a doubt,
modular
sir.
procedural programming.
Sir, actually, I'll take the same case.
Modular programming,
Regular
procedural
car, right, sir?
Okay.
Their power
object-oriented programming.
and the HP values are given.
Procedural
Assume they have given another attribute
Okay.
which has come
They are
lower
also
in the result. For example,
for problem
cost or
solving.
something, sir.
There are
Okay.
also different approaches for
Uh,
problem solving.
Power they have given, HP they have given,
Mhm.
and another attribute they have given cost, which has not come in the regenerate, the regenerate, sir.
Okay.
In that case, can I match 203 still with that regular car, sir?
So we can still match the individual elements, but overall, if even if there is one contradiction, we cannot say that that rule is applicable to be fired.
Okay. But that regenerate has not considered cost at all. But
Yeah.
it has come in the working memory elements, sir.
Where is the cost in the working memory?
No. Cost is not given anywhere in the work in the regenerate. But
Yeah.
I'm assuming that a cost is also attached to working memory model 203 or 204, whatever it may be.
Okay.
In that case, can 203 still be considered for a rule? For example, sir, I am assuming that regular car has considered 203, sir.
Let's say there is another element in over
Uh,
here, 211,
yes, sir.
that says cost of this car, let's say N34, is something like 5 lakhs. Okay. And let's say there is another attribute coming somewhere from this direction that says that the cost of a regular car must be less than 6 lakhs. Is this something similar to what you are asking?
No, sir. Sir, I say that because it has come in one of the questions, sir. It has not come anywhere in the
Sir,
regenerate.
actually in 207 it is there now, sir. Flat bed. So that is not nowhere in the retinet now.
No. I'm asking about an attribute itself.
Okay.
An attribute itself is not attribute which has not come in the regenerate, but has come in working memory, sir.
I see.
For example,
That might be an indicator of an incomplete working memory and an incomplete retinet. In that case, we can just ignore those points.
and can we still add 203? For example, sir, I'm assuming 203 is added to rule 3. Rule 3. In this case, now according to my question, there is an attribute cost which has come in 203, but it is not found anywhere in the regenerate.
I see.
Can
Yeah.
203 still come in R3? I'm asking, sir.
Yeah, we can do that because we have to confine ourselves with the retinet given to us. So
Yes,
we have to
yes.
assume that retinet is the only way for us to decide whether a rule will be fired or not. If
Yes,
that
sir.
retinet itself happens to be incomplete, that is something that is out of our hands.
Okay,
So we
okay.
just
So
have
that,
to make do with whatever is given to us.
okay. Thank you, sir. Thank you.
Okay, thanks for your question. Okay, then let's have a look at the other two options remaining in this question, which is minivan with two different set of elements. Okay, the first time we are considering 202 and 208. So let's check those. 202 says that there is a car H38 with horsepower 290, and 208 says that this H38 has limit 8. Now the preconditions for a minivan are that limit should be 8, which is satisfied, and that horsepower should be between 100 and 300. This is 290, so it just follows this, and so minivan can be fired. Do you agree with me?
Yes, sir.
Yes, sir.
Okay, now let's look at the last option, which is minivan with 203 and 9. So 203 tells us that N34 with horsepower 280 and passenger limit 4. But there is one violation over here, which is the passenger limit should be 8. So this particular instance of minivan cannot be fired. Agreed?
Yes, sir.
So when we come back to our answers, the elements that will be or the rule and element pairs or tuples that will form a part of our conflict set would be B, C and D. Okay, if that was clear, let's now move on to the next question. This question asks us to find the location in terms of alpha nodes where the token 204 resides. Okay, so let's look at what token 204 is. (204) tells us that there is some car K32 with horsepower 800. So we just have to tell where in which alpha node this particular fact resides. So as per the data net, which of these alpha nodes do you think would contain this fact? A car with horsepower 800.
A14.
A14,
Sorry,
that's right.
A13. A13.
Not A13, right? A13 is concerning the limit, passenger limit.
Yeah. Horsepower 800. Sorry,
Yeah.
sir. A12.
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 That's so actually it will be both A12 and A14.
Okay.
14. Yeah.
Yeah,
It will be better
because
than calculating.
yeah, in both of these
Yes, fine.
cases, the horsepower condition is being satisfied. So the answer will be A12 and A14. Okay, let's move on to the next question then. So now that we have identified what are the elements in our conflict set, we want to now apply different conflict resolution strategies to select which rule will be fired. Okay, so we remembered that the three candidates in our conflict set were luxury car 204, 5 and 10, regular car 203, 6 and 9, and minivan 202 and 8. So we have to choose one out of these three, and there are different ways to do that. Here we are asked to use specificity as the way to resolve the conflict, and what specificity tells us is that we will fire the rule that happens to be the most specific rule, or in other words, the rule for which we have to make the most number of checks in the preconditions of that rule. So which of these rules do you think would be chosen based on specificity? So in order to help you, let me actually mark these different candidates given in the conflict set. The first one is luxury car with 204, 5 and 10. So for that we have to check, this is one arrow, this is one arrow, this is one arrow. Okay, and this in turn is coming from here, this is coming from here, and this is coming from here and here. This is what we have to check for luxury car. Now let's change the color and have a look at the other candidate. The other candidate was a regular car. So for a regular car, we have to check this arrow, this arrow, this one, and this one, and these in turn come from here, here, this comes from here and here, this comes from here and here, and this comes from here and here. Now let's again change the color and look at the other candidate, which was minivan with 202 and 208. So for that we need to check this one, this one, this one. This comes from here and here, this comes from here and here, and this comes from here and here. So this is a way of checking specificity, as in how many of these different how many of these edges fall into the different color category. The more the number of edges, the more specific the rule is. So which of these rules do you think is more specific?
Minivan.
Minivan.
Are you sure? Check how many different colors of red, green and blue are there.
Regular car.
Regular car, that is right. Because see here, for regular car we have to check 4 conditions. First is type regular, then limit should be 4, then horsepower should be greater than 100 and less than 300. These are 2 separate conditions that we have to check. Whereas for the other 2, luxury car and minivan, we have to check only 3 conditions each. 1, 2, 3, 1, 2, 3. Okay. So this is one way of computing. Compute the sum of the path lengths. For luxury car, we have 3 plus 3 plus 3, which is 9 edges. Let me use the individual colors for that. So for minivan, we have 3 plus 3 plus 3, 9 edges. For regular car, we have 12 edges. And for luxury car, we have 9 edges again. So the most specific rule is this one. So this is one that will be chosen based on specificity. Is that clear? Any doubts there? Okay. If not, then that's great. Now let's have a look at another conflict resolution strategy, which is recency. Okay. So I'll give you a brief idea on what recency is basically. In order to test for recency, this is the test that we can follow. In a conflict set, for 2 conflicting instances of the same or different rules, recency is decided by listing the working memory elements in descending time sequence. This is important. And comparing the ordered list and selecting the dominant one. As an example, let's say we have 3 rules or three candidates in the conflict set. The first one is rule 1, let's say. Then we have rule 7 and then rule 2. Each of these, we first arrange each of these individually in the descending order of the timestamp of the elements that matched. So if you look at rule 1 alone, we have 210 first, then 208, then 207. Okay. Maybe you can mute yourself if there are no questions. Thanks. Similarly, in rule 7 we have 210 first, then 202, then 201, and similarly in rule 2 we have 209 first, then 208, and then 207. So within each rule the timestamps have been arranged in descending order. Okay. Now when we arrange these different rules, we will consider the first column of the timestamps first. So 210 is greater than 209. So rule 1 and rule 7 should be above rule 2. That is clear. Now in order to resolve which of rule 1 and rule 7 should be above each other, we will look at the next column. So here we see that 208 is greater than 202. So rule 1 will appear before rule 7. Okay, this is the way in which we have to arrange the different candidate rules and element tuples, and the one that is at the top will be chosen based on recency. So is it clear how do we actually use recency to resolve a conflict?
Yes, sir.
Okay, great then. So based on that, which of these do you think, which of these three candidates do you think would be chosen by the recency for conflict resolution?
Option B.
Sorry, can you come again? Remember, we have to sort them first individually based on the timestamps, then among each of them, then compare one to the other, all the other of them, and again rank them based on the descending order of the timestamps.
So I think the highest timestamp is 2210, sir. That is in two options, but I think both are having A and B. They are having the same thing.
So we won't consider A and E actually, because those are not part of our conflict set. Okay, in the previous question we established that the elements in the conflict set are B, C and D only. So
Okay.
those are the ones that we are going to concern ourselves with. So let us first rearrange these elements within them. Okay, so luxury car 210 will come at the front, right?
Yes, sir.
Then
Two luxury
205 and then 204.
Yes, sir.
Now let's arrange regular car.
209.
That's right. 209
206.
yeah, and then
And 6.
yes, and similarly for minivan 208 will be first, 202 will be after that. Now we should arrange all of these three candidates based on the first column of timestamps. So here we see that there is no issue in the first column of timestamps. It's a clear cut ranking where the topmost one is luxury car with 210, second is regular car with 209, and third is minivan with 208. So based on this ranking, luxury car is the one that will be selected based on recency as the conflict resolution strategy. Is that clear?
Yes, sir.
Okay, that's great then, and that also brings us to the end of questions for today. And I think we have also reached the end of the session today. Okay then, I hope some of the pending queries from the previous week, you might have gotten a chance to post that on the discussion forum. Have you arrived at some resolution for them, those who had asked the queries in the previous live session?
Yes, sir. There was reply given. The difference between the three things actually.
Okay,
Bhaskaran.
that's great to hear then. So if that is done, then maybe we can end the session today and then reconvene next week, same time, Tuesday 6 to
Sir,
yeah.
sir, I have doubt, sir.
Okay, if it's a quick doubt, we can discuss it right now.
Sir, without giving the retina diagram, sir, from working memory, can we find the alpha node?
No, we need to know the retinate, right? Without retinate, how will we decide where
So
the...
first we have to draw the retina diagram from the working memory. Then
No,
only you can find the alpha node.
usually in questions, retinate will be given to you.
No, sir. Retina is not given in the assignment question. Only working memory is given, but asking for the alpha nodes.
In that case, maybe yes, you have to construct the retinate. But
Sir,
usually in my
if you,
experience,
sir, that
retinate should
retina
be given.
diagram may be vary from person to person,
Ma'am,
no?
retinate is given, ma'am. Retinate is given.
difference கேட்டா சொல்லணும். Programs are divided into
Okay,
function.
maybe it is
Program are
given.
divided into
Maybe just
function.
have a closer look at the question. You'll find it then. Because yeah, even in my experience, RateNet is usually given because, like you said, different people might construct the RateNet in different ways, and that might lead to ambiguities.
Yes, ma'am. Actually, in begin group 4, retinet is given. That is the continuation, I think, up to the end. And from there only, this working memory has been derived.
Mm-hmm. So, okay, thanks for
That
the.
retinate will be used. No? That retinate will be used in that section.
Yeah, I think it might be a common RateNet for all the questions.
Okay, sir. Thank you. Sir, another
Sir,
question, sir.
sir, actually, a very, I mean, small non-technical question. Sir, in the final exam, can we expect a similar model, sir? Like, assume that if I practice well all these assignments and practice assignments, will that work completely?
Yeah, I think that is what I have been observing in the past couple of semesters, that the final exam will be very similar in the level of questions and the type of questions, quality of questions to the assignments that you practice, both as practice and the graded assignments. So if you understand and diligently do the assignments, the final exam should be relatively comfortable for you.
Actually, to be frank, assignment week 7 and week 6 are like comfortable, sir, compared to other assignments. But still, other assignments I mean, I have to work. These two assignments are okay, prologue and this retinet kind of thing.
That's okay. There's still time to practice before the exam, so that's
And
fine.
sir, apart from that, generally in NPTL, assume that if it is a 12-week course, do they follow any schema, sir? So from week 1, this many marks should be given, week 2, this many marks should be given, kind of thing.
Unfortunately, I'm not aware of that, but you can ask that in the forum. Maybe people
Okay, sir.
who set the questions, the NPTL team, may be more in touch with those kind of answers.
Okay, sir.
Thank you
Definitely,
so
sir.
much, sir.
Thank you,
Thank you,
sir.
sir.
Okay, then thanks all for attending, and yeah, let's meet next week.